Get static up. What's up, amigos? Today we're looking at how a wing flap system works. So we have a regular airfoil and we have two other elements behind it. So this is a three-element system effectively. The first part is the bulk of the airfoil. Then we have two smaller airfoils effectively that operate with the aerodynamics to increase the lift coefficient of this system dramatically. So to give you an idea of what wing flaps can do to the aerodynamics of a system, so a typical airfoil, the maximum lift coefficient you can achieve is probably around between 1.2 to 2, depending on how well it's designed. This system, which I've done CFD on here, you can see the streamlines, they can achieve, this is actually 3.16, the lift coefficient. Now the drag coefficient is also quite high, it's 0.155, which indicates that there is some stall, and we'll see later where that stall is occurring. But to have a lift coefficient of 3.2 is phenomenal compared to any other airfoil really. And the way they do this is through this system. So how does it work? So we have the typical airfoil over the front bit, and the air rushes over, and you can see that the flow is colored in the velocity from blue to red, red being 73 meters per second. So, and as you go over the top, it accelerates, we all know that. Then as we get to the trailing edge part of the first part of this system, the flow then starts to go over the other two sections, but if you look at the bottom streamlines, they start popping up and over these other airfoils. So let me draw your picture to illustrate what's going on. Just bear with me as I draw these things. So let's just have a two-element system. We have one airfoil here, and then have other airfoil we had here, let's say. It's just simplistic. And we have the flow going over the top, and it dives down a little bit. Then we have other flow underneath. Now this is the important bit. It gets to this point and then it shoots back up over this airfoil. And the reason why it's important is because the top flow here, this is actually slow moving flow by the time we get to this point. So it's really losing a lot of its steam in the boundary layer. What that means is if we were to continue to go over this other element, what this element will do to the flow will make it stall effectively, because this top part doesn't have enough energy to get over and stay attached. So by introducing this additional air and letting it bleed through this part here, the flow can then stay attached and produce a lot of lift. And in this system, we have another airfoil underneath as well, and we have even more flow coming up and under to re-energize this flow and have what's called a high momentum boundary layer. So we're just mixing a lot of high momentum fluid. So I mentioned that some of the airfoil is stalling. Let's talk about which part is stalling here. Okay, so we have this image here, and we have it colored. This is a slice now, so we can see again the velocity plotted, and it's very simple to see which part of the airfoil is stalling. It's obviously the third element. You can see there's a massive blue section there, which indicates very low slow moving fluid, and that indicates that the flow is not staying attached over the top, so it's not really producing much lift. However, it is producing quite a bit of drag, but it is still producing a little bit of lift, but not as much as, not efficiently. That's why we get such a high lift coefficient, but a high drag coefficient as well. We can reduce the lift coefficient, but then would reduce the drag coefficient as well. But if you want to get a lot of lift, you have to go into this configuration. So finally, we have a video showing the pressure. So this video here is the pressure plotted on the surface of the airfoil, and it goes from minus 1.5 by 10 to the 3 to 1.5 by 10 to the 3, going from blue to red, respectively. And as you expect, the top surface is very blue, and the top surface of every airfoil actually in this system is very blue. The undersurface is pinky red. So that means that the top surface is negative pressure, bottom surface is positive pressure. That's how you produce your lift. The good thing is that you can see that each one of these airfoil sections is producing lift by itself. So you know how I mentioned in the other video that the third element is in stall, but there is still a little bit of lift being produced, and you can see that here with the pressure gradients. So what does this mean? It means that because we are introducing additional air in between these little vents here, these little slots, we can treat each airfoil as effectively a separate lifting surface and still produce lift, so the entire system can reach such a high lift coefficient of 3.2. And you can get even higher, you can get to 3.4 and even higher if you really design the system very well. But as you can tell, it's very higher, very far above the average lift coefficient of an airfoil of like 1.2, 1.5, 1.8. So that's it in the simulation. Make sure to like, subscribe. And if you want to get better at CFD yourself and or theory like this, check out our courses in the link in the description. And I'll see you next session. Peace out, amigos.